Okay, today we're going to look at a few examples of questions dealing with buffers and pH. A lot of this deals with titrations as well. So some of these questions we've answered part of them or maybe all of them, but I want to look at them through the lens of a buffer and a titration. So on question number 56, and these are all in your homework packet, question number 56 says data collected during the titration of a 20 milliliter sample of a 0.0 molar solution of a monoprotic acid. Monoprotic just means one hydrogen, so like HA or HNO2, something like that. It just has one hydrogen that comes off. Okay, the data is collected in the graph above. Which of the following are the approximate pKa of the acid and the molar concentration of the NaOH? We're not too worried about the molar concentration of the NaOH, okay? We certainly can look, just real quickly, talk about that. If you look at the equivalence point right here, it happens right about here. So we're going to come down. That means we needed 20 milliliters of that base to reach the equivalence point. So if you have a 20 milliliter sample of a 0.10 molar solution of the acid, that means you have 0.02 liters times 0.10 molar equals 0.002 moles of the acid. That also equals 0.002 moles of the base, divided by, again, the 20 milliliters, 0.02. You can see that the concentration of the base is going to equal the concentration of the acid. So it is 0.10. Okay, more importantly, though, what's the pKa of the acid? So these are super duper easy. If you know the equivalence point is at 20, you know that at the half equivalence point, the pH equals the pKa. So at the half equivalence point, the pH equals the pKa, because remember, the rest of that log of A minus over HA these are equal to each other, so that cancels out. So pH equals pKa at the half equivalence point. So if the equivalence point is 20, the half equivalence point is 10, which means we go up to here, we go over, and it looks like it's somewhere maybe just right underneath 5. So if the concentration of NaOH is 0.10 and the pKa or the pH is 4.7, then again at the half equivalence point, the pH equals the pKa. The correct answer is B. Okay, and again, it all comes back to this idea of the pH equals the pKa when you're at that half equivalence point. Okay, let's jump to 58 here. Very similar type question. You've got a titration curve. The pH for the titration curve is shown below. On the basis of the pH curve, what's the pKa of the acid? So in this case, again, find the equivalence point right around, what happened there? Right around here, okay, and then go down. So the equivalence point is right around 25, which means the half equivalence point is half that volume. So there's 15. So about 12.5 would be here, come up, come over, and the pKa, or the pH is right around 5, which means the pH, or the pKa, is also right around 5. So the correct answer is B. Okay, and I'm not going to do all of these, so let's jump ahead to, let's see, 59. Okay, very similar. Which of the following could be the unknown acid, and what do? They give you the pKa values. So again, same thing, 25 down to 12.5, come up, come over. Looks like it's right around the high 3s, not quite 4, so therefore it has to be A. And again, because the pH equals the pKa at the half equivalence point. Okay? All right, let's look at numbers 60 through 62. So again, here's just a regular titration. We can see that the equivalence point was reached right at 40, which means at 20, we are again at the half equivalence point. So point S is the half equivalence point. And why is that important? because that's when the concentration of HA equals the concentration of A minus, okay? Before the half equivalence point, the concentration of the acid is greater than the concentration of the conjugate base. And then, of course, after the half equivalence point, we know that the concentration of the acid is less than the concentration of the conjugate base. Okay, now, why does that matter? Because I'm sure they're going to ask us some questions about that. So point T, we're past the half equivalence point. Therefore, at point T, the concentration of A minus is greater than the concentration of the acid. Okay, at point Q and point R, we're before the half equivalence point, which means the concentration of the acid is greater than the concentration of the conjugate base. Okay, so at point R in the titration, which of the following has the highest concentration? Well, first of all, you're definitely well down in the acidic region, so it's not going to be this. Okay, you have very little H plus, because remember, it's a buffer solution here, so it's definitely not going to be hydrogen ions. So now you're just deciding, what point in the titration am I? I'm before the half equivalence point. So therefore, the concentration of the acid is the strongest. So A is the correct answer. Okay, 61. Which of the following is the best particulate representation of the species other than water that are present in significant concentration in the solution at point U in the titration? So let's come back up here. At point U, we're well past the equivalence point, which means all of that acid is gone. You don't really have any of that HA left. So look at these answers here where you still have some HA left. Nope. Once you're past that equivalence point, all of that acid has reacted. And you're so far past it, this right here would be a great representation of the actual equivalence point where all of the acid is gone, but you don't have any leftover hydroxides. But at point U, where you're well past the equivalence point, see that you have that hydroxide left over? Absolutely yes. Okay? Now, going back real quickly, let's go back to these other answers. Answer C, notice that you have 2 A minuses and 2 HAs. I think you should know. What point are you at in that titration there? The half equivalence point, because the concentration of the acid equals the concentration of the conjugate base. Okay, and then certainly answer D, you've got mostly HA and you've got just 1 A minus. So at that, you're well before the half equivalence point. Okay, so here you're at the equivalence point, here you're at the half equivalence point, and here you're before the half equivalence point. And then 62, at which point on the titration curve is the concentration of A minus close to twice that of HA? And whether it's twice that or 1.5 times it, what's the only point on this graph where the concentration of A minus is greater than the concentration of HA? Okay, you might say, well, what about point U? No, the concentration of there is no HA left at point U. You can't say it's twice that amount. It's a million bazillion times more than that because there is no HA left at point U. So the only point where the conjugate base is greater than the acid is absolutely point T. Okay, at point T, you're past the half equivalence point. You now have more of the conjugate base than you do the acid. So it is at point T. Okay, and then on question number 64, lots and lots of, don't worry about most of this question. I just want to focus on one part of it. Notice here they tell you the value of Ka for sorbic acid is 1.7 times 10 to the minus fifth. And then we come all the way down here to part D, and it says calculate the pH at the half equivalence point. Okay, anytime you see half equivalence point, you've got to immediately think pH equals pKa. So, without doing parts A, B, or C, what's the pH at the half equivalence point? Well, the Ka is 1.7 times 10 to the negative fifth. So the pKa is the negative log of, pH is going to equal the negative log of 1.7 times 10 to the minus fifth. Okay? And that's all you've got to do on that question. The pH at the half equivalence point is you have to know the Ka value. You take the negative log of it to get the pKa value. and that is your pH. Okay, one more, and then we will stop. And some of these you've already done. So question number 70. Okay, question number 70, let's kind of go through, I think it's just these A, B, and C parts. So on question number 70, it tells you, write the expression for the equilibrium constant Ka. So Ka is going to equal, and again, you can write H plus or H3O plus, C9H7O4 minus over HC9H7O4. Okay, calculate the value of Ka. So it says the pH of a 0.010 molar solution is 2.78. So I know that's telling me the hydrogen ion concentration. So it's 10 to the power of negative 2.78 equals Ka equals 1.66 times 10 to the minus third. And that's going to be squared because those are going to equal each other. And then we're going to have the pH 0.0100. And remember to subtract that 1.66 times 10 to the minus third. It may not matter, but again, when it's not an x value, include it in there. So 1.66 times 10 to the minus third, I'm going to square that answer, and then I'm going to divide it by 0.01 minus 1.66 times 10 to the minus third. And I get a final answer in scientific notation of 3.30 times 10 to the minus fourth. Okay, and that is the Ka value. And then it says an aqueous solution of aspirin is buffered, buffer solution, to have equal concentrations of the acid and the conjugate base. Calculate the pH of the solution. If the concentrations of the acid and the conjugate base are equal to each other, then again, using the Henderson-Hasselbalch equation, the pH just equals the pKa. So that the log of the A minus over HA cancels out because it's equal to 1. The log of 1 is 0. The pH equals the pKa. So the pH is going to equal the negative log of 3.30 times 10 to the minus fourth. So the negative log of that answer equals a pH of 3.48 is our final answer on that. Okay, so those are just a few of the questions dealing with how do you use the Henderson-Hasselbalch equation when you're solving problems dealing with titrations and dealing with buffer solutions. Okay, and it's really that knowledge of at the half equivalence point, or when, or in this case, this isn't a titration at all, is it? Okay, but they do tell you you have equal concentrations of the acid and the conjugate base. Therefore, it's like even though you're not doing a titration at all, it's kind of like you're at the half equivalence point anyway, and the pH is just going to equal the pKa.